Pleasure for me to participate in this conference on phonons and condensed materials, and I thank Professor R.K. Singh for this invitation. Now here's a large number of friends at BAC. Dr. Kara is here because in the late 50s and the early 60s, the inelastic neutron scattering was a very, not that it is not now, at that time it was a very frontline and emerging field, and we had people P. K. Iyengar, G. Venkatraman, K. R. Rao, Dasanacharya, all these people there, and there was also a great deal of interest in theoretical lattice dynamics work, and that's why there was a close cooperation between Professor R.K. Singh's group and the experimental and theoretical group in the Bhabha Atomic Research Center. I'm also a condensed matter experimentalist, and down through nuclear magnetic resonance, neutron diffraction, and high pressure physics. And my neighbors in the Bhabha Atomic Research Center in the 60s were the phonon physics people, because we had the Cyrus reactor, then later we had the Dhruva reactor. And the very fortunate circumstance in thermal reactors is that the wavelength of the thermal neutron peaks around 1 to 2 angstroms. So that allows you to do structural work. And I was doing neutron crystallography. And it is also a fortunate circumstance that the energy of these neutrons, energy of these thermal neutrons, is similar to the energy of phonons in solids. So that you send the neutrons inside, exchange energy with phonons, and so it was one of the most powerful methods of studying lattice vibrations, which of course, as has been explained to you, including by an engineer there, that they are all quantized lattice vibrations. Of course, when you put it in a solid, the surroundings impose boundary conditions, and what is there, a vibron in a molecule or in an isolated systems becomes collective lattice vibrations and phonons. Phonon, as also a vibron, derives its restoring force from almost instantaneously and smoothly deforming the electron cloud that is within the Born-Oppenheimer approximation. And however, in metallic systems, phonons also scatter from electrons at the Fermi surface and cause things like electrical resistance, of impurities also do that, and thermoelectric power and so on. At a more fundamental level, this electron-phonon interaction is also responsible for the property of superconductivity, at least in low temperature superconductors, conventional superconductors. Phonons may also interact with other phonons due to anharmonicity, and these interactions bring about changes in various line shape parameters of phonons at the basic level and thermal expansion at the more gross level. Though the essence of these interactions is by now well known, the specific nature may depend on the atom surrounding the solid, the structure, temperature, pressure, and other external fields. Historically, the concept of the phonons was necessary for Debay's theory of specific heat of solids, but a better understanding of phonons emerged after inelastic neutron scattering technique helped to determine the dispersion curves. Now, this technique is routinely used for the determination of dispersion curves as well as density of state of the phonons, though calculating in complex crystals, certainly in quasi-crystals, it's not possible to get accurate dispersion curves. That is where I saw one of the posters from the Saha Institute of Physics, Nuclear Physics group, and where they are describing their positron annihilation setup. Of course, positron annihilation is a powerful method of studying vacancy defects in solids, and had always been bothered by this Penrose lattices for models for quasi-crystals, because in a rapidly solidifying situation, if the nature did not organize itself into a structure with one unit cell, why would it bother with two? And in the case of the Penrose lattice, the very strict matching rules. And that is why, that is Bhopal, I remember, I and Prashant Sen, we got together to discuss and we had a lot of work, and that led to a model I have proposed on what I consider as icosahedral cluster and disordered blue model for quasicrystals. More recently, synchrotron radiation is beginning to be used for inelastic scattering, and thus for the study of phonons. Obviously, this requires excellent collimation as well as very high brilliance, such as an undulator. My colleague Surendra Sharma brought to my attention a piece of work on the dispersion curve of diamond. This came in the physical review last month, which shows that the inelastic neutron scattering as well as inelastic X-ray scattering are both important, and both can be now studied with comparable accuracy. And they found to an overbending of the longitudinal optical phonon branch. I'm mentioning this because when I did my PhD in the Indian Institute of Science, my professor was R.S. Krishnan. And as early as 1946 and 1947, R.S. Krishnan had shown that there is an anomaly in the second order Raman spectrum, and this was shown for the first time. And this seems to have been now explained by the work that I was mentioning to you on diamond. Of course, Raman active, the zone center Raman active and IR active phonon modes are measured routinely using Raman scattering and IR absorption. Initial efforts in this field were driven by the need to validate concepts as well as for a better understanding of inter or intramolecular forces. However, the dynamics also plays a vital role in determining the stability of the phases under different thermodynamic conditions. One obvious relation is that the vibrations contribute to entropy and hence to the free energy. It may so happen that two structural phases are related to each other through correlated atomic displacements represented by a phonon mode. For example, beta tin phase of silicon is related to the primitive hexagonal phase. This happens at about 15 GPa, and through the atomic displacement characteristic of the zone center phonon mode along 101. Such relationships between structures are then explainable in terms of soft mode picture and relate well to the emergence of order parameters in terms of Landau theory. However, whether even for a perfect second order phase transformation, a phonon mode fully softens or not is still an open question. Softening of the mode may be partial, and the primary order parameters such as displacement of atoms due to the softening mode may be coupled to other order parameters. And this has been seen, and in fact I think we saw it for the first time in cadmium mercury alloys. This homogeneous strain and shuffle displacements corresponding to a phonon being combined. It's like having two order parameters in a modified Landau theory, and which are coupled. And none need to fully soften to bring about a phase transformation. In recent years, even the role of softening of modes in the pressure-induced crystal to amorphous phase transformations has been proposed. Sikka and his colleague Sharman have written a very good review article, I think in Physics Reports, on this. However, to bring about an amorphous phase transformation, a large number of modes, perhaps a branch, will have to go soft. Nanocrystalline materials was mentioned here, and this is another very interesting emerging topic. And here, of course, the question of phonon localization has also opened up. One end you have the theoretical techniques, at the other end you must have adequate computational facilities, and now with parallel processing computers, many groups have access to supercomputing power. Computations of dynamics has also undergone a substantial change in the recent years. In contrast to the earlier, the force constant approach, derivable from the classical pair potentials, Present-day calculations are based on first principles. In these calculations, electron states are computed through the local density functional theory. This we have done routinely at, we are able to do it at high pressures. The forces required for the dynamical matrix are obtained using Hellman-Feynman approach, leading to the first principle evaluation of dispersion curves. Obviously, this transcends earlier frozen phonon approach for the first principles calculations, which permitted evaluation of only some phonons at the high symmetry points in the Brillouin zone. So let me close with one quotation by the famous biologist Peter Medawar. Peter Medawar was a Nobel Prize winning biologist, and he's written an excellent book called Advice to a Young Scientist. And his advice is very simple: always work on important problems. Now the question is, how do you decide what is important? This is where the group in which you work. He says any problem studied in sufficient depth becomes interesting. It's not good enough. It has to be important to science and or important to society. So the focus, now phonon physics and the experimental techniques used for studying have come of age. It's no longer in one of those subjects in which you can take any problem and do it, it becomes, and then it becomes a publishable material. Today, one has to focus on the problem, the importance of the problem, either basic interest or in terms of its possible application of the material concern. And let me say once again how happy I am to participate in this meeting. Thank you very much.